Hey everybody, sorry I couldn't be here today. I am at home with my kids while my wife attends a funeral, which means I may be able to answer questions. If you have specific stuff going on, you can just send me a Teams message. But hopefully, today's notes will be pretty straightforward. You can just watch the video and maybe even get your homework done before the weekend. Let's start by looking through the 4.2 homework. The key will already be in your content library, so you can just go check against that, or you can watch through this video to see the specific answers to all of these questions. So number 1, sulfur is a nonmetal because it's on the right side, and it has 1, 2, 3, 4, 5, 6 valence electrons. Rubidium is way over here. It is a metal, being on the left side of the zigzag line. It has 1 valence electron. Beryllium is also a metal. It has 2 valence electrons, being in group 2A. And iodine right here is a nonmetal, right side of our zigzag line, and it has 7 valence electrons. Now, in order to get through number 2 quickly, I was thinking I might just highlight all the metals that I see. Mercury is a metal, calcium, sodium, calcium, these are both nonmetals. Magnesium, lithium, iron, these are both nonmetals. Hydrogen, sulfur, oxygen, all nonmetals. CHO, copper is a metal, aluminum is a metal. Sulfur and oxygen are both nonmetals. Carbon and chlorine are both nonmetals. Strontium is a metal, fluorine is not. Any compound that includes a metal and a nonmetal is going to be ionic. Unless my pen stops working. Ionic. Any compound that only includes nonmetals, carbon and sulfur, nitrogen and iodine, all of these are covalent. All right, moving on. List the expected charge for each of the following ions. Remember, substances that have 1 valence electron are likely to have a positive 1 charge. Substances with 2 valence electrons will always react in a way where they lose those 2 electrons, giving them a positive 2 charge. Positive. Hold please. Positive 2. We don't know about these guys. Mess with them later. These will be positive 3. These will be plus or minus 4. And then we go negative 3, negative 2, negative 1, 0. Fluorine has 7 valence electrons. It will always gain an electron in a bond. That would give it a negative 1 charge. So I just find each element. Magnesium, right here, is always going to have a positive 2 charge. Mg2+. Potassium is always going to have a positive 1 charge. And by always, I mean if it becomes an ion, it will be a positive 1 ion. Boron, plus 3 charge. Selenium is a minus 2 charge. Aluminum is a plus 3 charge. Tin, Sn, is a plus or minus 4. Now this one is special because in our notes we said that the metals to the right side of the transition metals, so this group right here, will often act like transition metals. But you will know, based on context clues, whether it's going to do that or not. So we can always come back to that later. Number 4, for each pairing below, circle the element that's likely to steal electrons in a chemical reaction. Who steals electrons? The nonmetals. Sodium versus iodine. Sodium is a metal. Iodine is a nonmetal, so iodine's likely to steal. Phosphorus versus bromine, both of these are nonmetals. They will both try to steal, and that will cause them to end up in a covalent bond. Nitrogen and potassium. My nitrogen is my nonmetal. It will steal from potassium. And then copper and zinc. These are both metals. Technically, they'll both try to steal, but they'll both kind of share as well. This will be a metallic bond, and I'm not going to circle either one. Another way to ask question number 4 is to say, circle the nonmetals. All right, and then second page, all of these Lewis dot diagrams. It is very important to know whether the bond is going to be ionic or covalent. So let's just go do that first. Carbon and hydrogen are both nonmetals, so this is going to be covalent. Hydrogen and oxygen are nonmetals. Carbon and oxygen, all nonmetals. Nitrogen and chlorine, nonmetals. Magnesium is a metal. Sulfur is a nonmetal, so this will be ionic. Sodium is a metal. Oxygen is a nonmetal, so this will be ionic. So remember, ionic Lewis dot structures involve ions in brackets. Covalent Lewis dot structures have the dots and dashes, the bars that show us bonds. So how do I work this out? Carbon has, right here, 4 valence electrons. 1, 2, 3, 4. The formula tells me that I need 4 hydrogens. Each of them will have 1 valence electron. Carbon would like to steal 4 times to get up to 8. Hydrogen is unwilling to let go. So you end up with something that might look like this. The only reason I switched it from being in a plus shape to an X shape is because the X shape fits nicer. It doesn't make any difference how you draw these. The angle is unimportant. H2O. I have 2 hydrogens and 1 oxygen. Oxygen has 1, 2, oh, hello. 1, 2, 3, 4, 5, 6 valence electrons. Each hydrogen has 1. The hydrogens can only steal 1 time. The oxygen would like to steal twice. And you end up with a bond that'll look like this. Later in the year, we'll discuss the importance of drawing the correct angles on these. Man, my pen is not working again. Here we go. If you drew this in a straight line, something like this, that is also fine. Technically, the way I drew it is the most correct, but I'm just interested, do you have 2 bonds and 2 lone pairs around the oxygen? What matters is that hydrogen has a full shell of 2 electrons, represented by the bond, and oxygen has a full shell of 8 electrons, represented by 2 bonds and 2 lone pairs, 2, 4, 6, 8. Carbon dioxide, I have a carbon and 2 oxygens. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Oxygen wants to steal 2 times. The other oxygen also wants to steal 2 times. Carbon wants to steal 4 times. So if I count, does everyone have a full valence shell at this point? Carbon has 2, 4, 6, 8 with all these bonds. The oxygens have 2 lone pairs and 2 bonds. So that is still good. Your final result will be oxygen double bonded to carbon, double bonded to oxygen on the other side. And you have 4 valence electrons, 2 lone pairs on each oxygen. NCl3, this is going to end up looking just like NH3 from your notes, except for a whole lot more dots around these chlorines. Chlorines have 7 valence electrons. Nitrogen has 5 valence electrons. That means nitrogen wants to steal 3 times. Each chlorine only wants to steal 1 time. In order for everyone to have a full shell, you end up with a molecule that will look like the following. There we go. Nope. One, two, three, four, five, 6. 1, 2, chlorine. All right, now we switch to our ionic bonds. Magnesium has 2 valence electrons. Sulfur has 6. The strong nonmetal will steal until it has a full shell. Magnesium is down to a full shell, so the correct final answer will be magnesium with a positive 2 charge, and sulfur with 8 drawn electrons and a negative 2 charge. Sodium has 1 valence electron. My formula, go ahead and hints that I'm going to need 2 sodiums. Oxygen has 6 valence electrons. Oxygen is going to steal from sodium and also steal from the other sodium. My final answer would be 2 sodium ions. Each one has a positive 1 charge, and 1 oxygen ion with its 8 dots, and that 1 oxygen ion has a negative 2 charge. Again, if you have any questions about any of these homework problems, feel free to send me a Teams message. Okay, we're going to jump straight into the notes for today. Nomenclature is the set of rules used to name compounds. We've been throwing names around, carbon dioxide and sulfur hexafluoride and all these different things. The way those names are created is there were systems put in place with specific rules and formulas for how to turn any given molecule or formula unit into a special name. And there are always things that break those rules. And by break, I mean if something like water already has a name that everyone understands, you might just choose to call it water rather than the official formulaic name, which we will get to in a moment. We're going to start with ionic compounds, and here are your 4 steps for naming an ionic compound. Ionic compounds always have a metal and a nonmetal, so you'll start by simply naming the metal. So here I have sodium and chlorine. If I want to name the metal, I will say sodium. Then it says name the nonmetal with its elemental name and an "ide" ending. So chlorine is my nonmetal. I need it to end in "ide" to show that it's a compound. So NaCl, sodium and chlorine, would be called sodium chloride. This has to do with transition metals. This has to do with something called polyatomic. We'll get to those in a moment. Barium and iodine. I name the metal barium. I name the nonmetal, allowing it to end in "ide." iodide. This is barium iodide. We can just keep going through. The metal is magnesium, the nonmetal is nitrogen. So this would be called magnesium nitride. You'll notice that I'm completely ignoring the numbers in all of these naming conventions because, like we said yesterday, or last class, sodium will always have a positive 1 charge. Chlorine will always have a negative 1 charge. So the only way to combine sodium and chlorine is to have 1 sodium for every 1 chlorine. Therefore, I don't have to tell people how many sodiums and chlorines make up this crystal because there's only one answer. It's always 1 to 1. Now, copper is a transition metal. Step 3 says name transition metals by using Roman numerals to indicate the charge. So in order to name copper and chlorine, I have to know what kind of ion this copper is. And the way you do that is by remembering that a formula unit is always neutral. So I'm just going to do some work underneath. I've got copper over here, and I have 2 chlorines. Chlorine, right here on the periodic table, has 7 valence electrons. It will always have a negative 1 charge. That means between my 2 chlorine ions, I will have a negative 2 charge. In order to have a neutral formula unit, my copper has to have a positive 2 charge. As a result, what kind of copper do I have? I have copper 2, and then I follow the rest of the convention, chloride. Now, sometimes this can get a little bit complex if I look at iron and oxygen right here. I have 3 oxygens. Each one, oxygen's right here, every oxygen will end up with a negative 2 charge, which means I have a total of negative 6. I have 2 irons, and they will require a total of positive 6 in order to cancel it out. For 2 irons to have a positive 6 charge, that means each individual iron will have a positive 3 charge. This specific substance is called iron, come on pen, iron 3 oxide. I name the metal. Since it's a transition metal, I give the charge for that particular type of iron, and then I give my nonmetal ending in "ide." Now, tin, Sn right here, would normally be considered to have a plus or minus 4 charge. However, because it's a metal to the right of transition metals, it might be acting like a transition metal, and we can double check that. My oxygen will always have a negative 2 charge based on where it is on the periodic table. As a result, a single tin has to have a positive 2 charge. That means it's not behaving the way the other elements in its family might behave. It's acting more like a transition metal. So this is tin 2 oxide. Okay, so following the rules, regular main body ionic substances, you name the metal, you name the nonmetal ending in "ide." Transition metals, mildly more complex, you name the metal and give the charge of the specific ion you're using based on how it's neutral, and then give the nonmetal ending in "ide." Now, the last rule in our ionic has to do with how to name a polyatomic ionic substance. A polyatomic ion is actually a special kind of covalent molecule. Poly means many, and so a polyatomic ion is a many atom ion. It is one atom, but it is made out, or no, it is one ion, but it is made out of several atoms that are charged like an ion. over here we have a list of common polyatomic ions. So CO3 right here, carbonate. Carbonate is going to be a carbon that is connected to 3 oxygens, might look something like this. And you'll notice that the carbon, this is not an actually correct Lewis dot structure, but it'll be a covalent molecule, but the entire molecule has more electrons than it has protons. If I add up all the electrons in the molecule and all the protons in the molecule, I end up with 2 extra electrons. So the carbonate molecule has a -2 charge and will behave like a negative ion. So ionic compounds still only have 1 cation and 1 anion, but those cations or anions might be made up of many atoms bonded covalently. The cation is always going to be one metal by itself or a positive polyatomic ion like ammonium. Ammonium is the only positive ion, the only positive polyatomic that we work with in first-year chemistry. The anion is always going to be made up of one nonmetal or a polyatomic ion. You'll notice most of these in here have a negative charge, where ammonium is the only one with a positive charge. You won't be expected to memorize this list of ions, but you do need to be very familiar with it. You need to be able to know when a group of atoms looks like one of these polyatomic ions. The way that we name these is nice and simple. You just name the metal and then name the polyatomic ion. So when I look at this, the first thing I'll notice is calcium is a metal, and then I see a bunch of nonmetals. So I'm going to say, oh, this must be an ionic substance. And because I see a whole bunch of nonmetals on the right, it must be a polyatomic ion for the anion. So I name the metal calcium, and I name the polyatomic ion CO3 is right here. It's called carbonate. Calcium carbonate is the name of this substance. And that's as simple as it needs to be. The metal for this second one is sodium. I see multiple atoms making up my anion, so I go find it on the list, and it is called hydroxide. This substance is sodium hydroxide. Magnesium is the name of my metal. I see multiple atoms, so I think that's a polyatomic ion. I find NO2. Be careful, don't get NO3 and NO2 mixed up. NO2 is called nitrite. Nitrite. TE. Come on, pen, work with me. Now, while I'm waiting for my pen to work, I want you to notice the nitrite has a 2 next to the oxygen and a 2 off to the side. What that's telling us is that I have 2 copies of that specific anion. So effectively, I have magnesium with its +2 charge. Come on, pen. One second, I apologize. All right, I'm back. Let's see if this works better. So magnesium always has a +2 charge. Nitrite, you see over here, has a -1 charge. And so let's put these in brackets. Nitrite, NO2, has a -1 charge. The other nitrite will also have a -1 charge. And so you end up with magnesium and 2 separate nitrites. That's why the NO2 has a 2 next to it, combining to form one formula unit. All right, And then this last one, this time I technically appear to have all nonmetals, and so you might think that this is covalent, but the way that it's written out, it should lead you to think, this seems to be ionic, especially if you just are familiar with NH4 is ammonium. So I have 2 ammonium ions, but the rules are just name the cation, ammonium, and then name the anion ending in "ide," unless it's a polyatomic where you just write the name of the polyatomic. Okay, so the ionic is actually quite a bit more complex than the covalent, so that means at this point we're done with the hard part. Let's come down here. Sometimes you might need to go the other direction. What if I just give you the compound name lithium bromide and I ask you to give me the formula unit? Now, there are a few different ways that you can do that. Let's work through all the different possibilities. The first thing we want to know is what is the charge of both of my ions, because my final formula unit needs to have a neutral charge. So I come over to the periodic table. Lithium always has a +1 charge. Bromine always has a -1 charge. If these two charges match, then right away we know I only need one of each because those numbers already cancel out. So lithium and bromine +1, -1, they already cancel out. The formula unit for lithium bromide is LiBr. And there's really no more work that I need to do. Let's look at another example. Magnesium, right here, has a +2 charge. Phosphorus, phosphide, has a -3 charge. Having one of each is not going to cut it for us. Now, one thing you can do is do the Lewis structure work like we did yesterday. You draw magnesium with its valence electrons, you draw phosphorus with its valence electrons, and you go back and forth having the phosphorus steal, and then the magnesium needs to show up more until you figure out how much you need. But there are other ways to do that. In fact, let's just do it that way. We'll zoom in. Show you a bunch of different ways you can get to your final answer. Magnesium has 2 valence electrons. Phosphorus has 8, 7, 6, 5. 1, 2, 3, 4, 5. The phosphorus is going to steal twice, and then I need more magnesium. Phosphorus is going to steal one more time, and then I need more phosphorus. 1, 2, 3, 4, 5. Gonna steal just once, and then I need more magnesium. 1, 2. It's going to steal twice. And at this point, everyone is happy, and I see that I need 3 magnesiums and 2 phosphoruses. Now, there are 2 other ways you can work this out. One of them is very mathy. I have magnesium and phosphorus. Magnesium has a +2 charge, phosphorus has a -3 charge. And I can ask myself, between 2 and 3, what is the least common multiple? My multiples of 2, 2, 4, 6. My multiples of 3, 3, 6, 9. The least common multiple is 6. That tells me that I need a total positive charge of +6. And I need a total negative charge of -6. So how do I get magnesium to a +6 charge? Well, I need 2 magnesiums. How do I get phosphorus to a -6 charge? I need 2. Oh, no, I did that wrong. 2 times 3 is +6. How do I get phosphorus to a -6 charge? 3 times 2 is -6. This gets me to the same answer, 3 magnesiums, 2 phosphoruses. And then the last way I can show you is called the crisscross method. MGP. You start by writing out your substances with their charges, and then you simply crisscross to take the charge and add it to the, you take the charge and crisscross the numbers so that the negative charge becomes the number of cations you need, and the positive charge becomes the number of anions that you need. 3 magnesiums and 2 phosphoruses. Now, the downside of using the crisscross method is you might need to simplify. The formula unit must be the lowest ratio. That means if you do the crisscross method and you get something like 2 and 4, then you need to divide both of those numbers by 2 so that you have 1 and 2. We'll keep playing with these different methods as we go through the rest of the notes. But we've just seen that I need 3 magnesiums and 2 phosphoruses. Mg3, P2. All right. Barium sulfide. Barium has a positive 2 charge. Man, when I'm recording, this pen likes to stop working. Coming back over here, barium has a positive 2 charge, and sulfur has a negative 2 charge. So right away, I told you if those things match, that tells you that you just need 1 barium and 1 sulfur, because they will cancel out. If you choose to do the crisscross thing, then you will crisscross, boop, boop, and you will see that I'm supposed to have 2 of each, but the formula unit must always be the lowest ratio. Both 2's are divisible by 2, and so if I divide that by 2, I get 1 barium and 1 sulfur. The correct formula for barium sulfide is BAS. Continuing through, lead 4 oxide. This 4 right here tells me that the lead has a positive 4 charge. Oxygen has 6 valence electrons, so it will always have a negative 2 charge. Lead is Pb plus 4. Oxygen is O. When it writes for me, everything is frozen. Sorry, guys. With a minus 2 charge. If we're going to follow the crisscross method, I put a 2 next to lead, I put a 4 next to oxygen. This can be simplified, so it must be simplified. Both numbers are divisible by 2, so that tells me I need 1 lead atom for every 2 oxygen atoms. PbO2 is the final answer. Finally, aluminum nitrate. Aluminum has a positive 3 charge, according to my periodic table. Nitrate, notice this does not end in "ide", it ends in "ate". Most of our polyatomic ions end in "ate" and "ite", so I need to go back up here to this list and find nitrate. Nitrate is NO3, and it has a negative 1 charge. So we'll just make ourselves a note. Nitrate is NO3, and it has a negative 1 charge. So aluminum has a positive 3 charge. Nitrate, NO3, has a negative 1 charge. When I crisscross, I need 1 aluminum and 3 nitrates. Remember, the 3 that's already there is part of the nitrate. It's baked in. Nitrate means 1 nitrogen and 3 oxygens. And for this ionic substance, we need 3 complete nitrates. Now, 1 and 3 are not divisible by anything, so it's already simplified. So my final formula will be 1 aluminum and 3 nitrates. Okay, how long have we been going? Do I have a timer on here somewhere? 35 minutes. Cool. Covalent should be relatively quick to get through. How do we name molecules? For most ionic substance, and so by most I mean everything except for the transition metals, the atoms only form one ion, and so they'll only react in one way. Sodium and chlorine can only form one substance, sodium chloride. For covalent substances, this is not the case. The same ingredients can create a bunch of different molecules depending on how they're formed. Remember last class we had all those C's, H's, and O's forming all different kinds of vitamins? Covalent can get really complex and really unusual. Here's just a way to describe that. If I am combining just hydrogen and just oxygen, if I have 2 hydrogens and 1 oxygen, H2O, this makes water, which is a clear liquid necessary for life. But if I change the formula just a little bit and I have 2 hydrogens and 2 oxygens, H2O2, now we call it hydrogen peroxide. Pure hydrogen peroxide is kind of a bluish liquid. If you drink it, it can explosively expand in your stomach and kill you. Straight up kill you. So, H2O keeps you alive, H2O2 kills you dead. What if I have too many hydrogens? H3O. This is a specific polyatomic ion that's called hydronium, and it is responsible for the destructive properties of acids. So too much hydronium will melt your face off. Therefore, it is really, really important when you're telling somebody that you have a molecule made of hydrogen and oxygen to also tell them how many hydrogens and oxygens you have, because that can be literally life or death. We do that with prefixes. And here are all of the prefixes. The prefixes for 1 is mono. The prefix for 2 is di, like carbon dioxide. The prefix for 3 is tri. The prefix for 4 is tetra. The way that I remember this one is from the game Tetris. I don't know if you've ever noticed, but all of the blocks in Tetris are made out of exactly 4 squares. In the original game, every block has 4 squares. I always mess up trying to draw this one. 1, 2, 3, 4. These are called tetrominoes because tetra means 4. 5 is penta. 6 is hexa, like a hexagon. 7 is hepta. 8 is octa. 9 is nona, sounds like 9. And 10 is deca. So, by putting these prefix words before the name of an element, you're telling people precisely how many of that element are in the molecule. When I'm naming a simple covalent molecule, I name the first nonmetal using a prefix. I name the second nonmetal also using a prefix, and then you end in "ide." The only one exception is we never start a molecule with the word mono. Not sure exactly why, but we just assume that there's only one at the beginning unless you have a prefix. So, I have 1 carbon and 2 oxygens. So let's go ahead and write in all of the prefixes. If I have 1 carbon, that would be called monocarbon. If I have 2 oxygens, that would be called dioxygen. But I always need to end in "ide." So monocarbon dioxide. But we never ever start with mono. So this is called carbon dioxide. If I have 2 nitrogens, we call this dinitrogen. And I have 3 oxygens, so we call this trioxygen. But we always end in "ide, so it's trioxide. dinitrogen trioxide. Here I have one carbon, monocarbon, and I have one oxygen, monooxygen, but I don't end in oxygen, I end in oxide, and I never ever start with mono. Oh, you're not going to let me scratch that out? So this is called carbon monoxide. Going in reverse, I don't have to count any charges because covalent molecules don't have charges. So if I see dinitrogen, that tells me I have 2 nitrogens. If I see pentoxide, that tells me that I have 5 oxygens. Chlorine monofluoride. Chlorine by itself tells me I have 1 chlorine. Monofluoride tells me I have 1 fluorine, ClF. And finally, dihydrogen monoxide. Dihydrogen tells me that I have 2 hydrogen molecules. Monoxide tells me I have 1 oxygen molecule. And this is the officially correct term for describing the water molecule, dihydrogen monoxide. Now, your homework is going to be a bunch of this nomenclature practice for covalent and ionic molecules and formula units. How do I name them? How do I write the chemical formula if I've given the name? If you want extra help, this link right here is a playlist, a full playlist. There's like 6 or 7 videos, each about 10 minutes long, from Tyler DeWitt, and he just carefully breaks down a bunch of different things. If you're struggling with the transition metals, he has a video for that. He also has a video all about naming acids. We are not ready for that yet, so you can just skip it until next semester. Last thing, please let me know if you have more questions. I should be able to answer Teams messages on and off. All right, cool.